And if you look at the bottom, you'll see the participants, the number of people on the call rapidly increasing as the system lets everybody in. So, so as you were saying, Keith, you know, very much the developing the standards goes very much hand in hand with improved practices on the airfield. So, provided, I mean, one of the things that, you know, Tony's always said, if the standard of AGL maintenance improves, then the requirement for that many airfield lights and the shallow and the close spacing also can be relaxed. So there are benefits. There are actual benefits of good maintenance. It's not just being beaten up by regulations, isn't it, Tony?
Yeah, but it's not only.
Yeah.
Sorry.
I think the thing was about simplifying the approach and runway lighting was that part of that was driven by economics. You know, we did the research to see if it was feasible because of considerations of, you know, ecology, you know, less energy being used, fewer fittings to maintain and so. The only people that lose out are the fitting manufacturers.
Right. Okay, well.
They don't sell so many, but apart from that, it is actually a win-win, and we show quite conclusively that you know what was the standard was over-egging it if you did decent maintenance and with better understanding of what was required in low visibilities. The patterns were proposed in the late 1950s on the assumption that they would be adequate and more. We were able to look at what was sufficient, and all was sufficient, even in failure modes. I mean, we looked at what happens if you've got a 30-meter space center line and you fail it to 60, you know, you lose one of your interleaving circuits, so you go to 60 meters. And the most critical thing is actually the takeoff. When you've gone past V1, you're committed to continue the takeoff, and you haven't got the V2 rotate. With a heavy airplane, that can be quite a long time, and you've got to keep the thing straight. And we showed conclusively that the pilots didn't have a problem with that. Mm-hmm. So you can have 30 meters in any visibility, actually, and know you might have a failure that takes you to 60 meter space, and it's still quite safe.
Right. And so you agree with that, Keith?
Very true what Tony has just mentioned there, because the people who lose out, as we said, are the suppliers, and I think it comes back to when we're looking at design, then the way projects are actually given out, and something we could discuss later or at a different time, is that is it just a design function, or is it a design and supply function? Is it a design, supply, and install function? Then clearly, when you go past the design element and then into design and supply, install, etc., then the suppliers then have a vested interest to select a design appropriate for their products.
Of course.
The independent designer is more practical and probably a more sensible approach.
I agree.
Whilst there's a need for the regulations to evolve with best practice, the technology is evolving, as well as the role of the designers and the tools available to the designers, the installers, the maintainers, and of course the regulators. So I guess it's just evolution. The only problem is, of course, the regulations somewhat lag that, because I think the processes to support the updating of regulation are I mean, I think does it come down to just the issue of funding and resources? Why don't the regulations keep up with developments in the market? Tony.
Well, Tony maybe is better to answer this, but for my my experience is that, remember, the regulatory details that are issued by ICAO is a consensus, right? And it has to go through a long process. And that consensus basically then gets pushed out to all the countries worldwide, and that is a time-consuming thing. So the process is quite long-winded, I would call it, to try to get, you know,
Don't tell me.
approval globally, eh? And Tony's
5 years is 5 years is rocket science for them.
and I hope everybody who's listening now is 5 years is rocket science. Did you hear that? Eh?
Yeah, but it is down to, it's all of our responsibility to push for this. If we, you know, we can all, you know, as a small group, we can see the need. We benefit from it. It is at the core of what we do, safety and compliance, and we just have to put in the investment in time and effort, and very much industry needs to do that, play its part in that, because industry has some, you could argue, the most to gain, but also has the resource to be able to support that. So it does need some focus and some resources invested in that direction. But hopefully, you know, that some of these webinars will be thought-provoking and will stimulate, you know, some of our audience to contribute. Certainly, we're happy to work with anybody in that vein, and we ourselves have taken up an initiative, an invitation to work with the visual aids group to propose some, you know, to put forward some suggestions as to what we would like to, areas we might see could be improved on, even though we accept it will take a period of time. Perhaps we could even do a webinar with our thoughts one week. I don't know. What do you think, Keith?
Well, that'd be quite a good, I think the sharing of information. I think very principally, everybody really wants the same thing. We want to be able to sit in an aircraft, and we need to be able to sit in an aircraft that moves safely along the ground to the runway, takes off safely, transits through the air safely, and approaches and lands safely, and then transits along the ground to the parking position so we get off safely. That's what every single person in the world wants. How we achieve that, then that's a little bit more difficult, of course, you know, but that's the reality. It's about safety. And I think we've all got a shared reason for that. And so sharing information is part of that process.
I think there's a thing, talking about annexes and regulations and so on. The visual aids panel, its remit was to write the requirements in terms of operational requirements. In other words, the approach lighting needs to be this pattern and have these beam spreads and these colors. It tried not to, and it was against the idea that we would, rather like the FAA do, tell you what size nut and bolt you use to do it, because that way, it tends to be reflected more in the design manuals. What you tend to do there is stifle technological development, because you enshrine your requirements, not in Annex 14, but in other documents. You write them down, and they're there for 40 years, and you've got technology developments coming along, which you stifle by that. And that was quite deliberate as far as ICAO is concerned. We were saying, this is what needs to come out of those lights, if you like, and where they need to be pointed. So it's up to you to decide how you're going to do it and use appropriate technology. Now, I know the FAA are much more prescriptive, and, you know, the length of bolt, and the size of the bolt, and the color of this, that, and the other. Less so in Europe, but there is that distinction. Sometimes I think it's misunderstood, and that's why the ADMs in particular get out of date.
think that's
Which
where,
is,
Tony, I think one of we're on it still in the discussion points here, is where the IEC, the International Electrotechnical Commission, with their technical specifications, and the Technical Committee 97, which is dedicated for AGL,
Yeah.
then their document 61820, and which is in some ways pretty much a mirror image of all the ICAO documents, and there is a review of that document to combine lots and lots of things together, and that of course is that process with TC 97 again takes time, but potentially is a little quicker than the ICAO.
Yeah.
right. Well, look, it's now 2 o'clock, so I think it's time to kick off. So thank you for that. Welcome to everybody to today's TMS Tuesday. The subject is Airfield Ground Lighting, the design methodology, and it's presented by John Lahiff. We have today on our panel Keith Costel, who is Director of TMS Training Solutions and well known to you as a well-renowned trainer and expert in airfield lighting. Tony Smith, Fellow of the Royal Institute, creator of a lot of the standards to which we now comply, authority on airfield lighting, and very welcome, Tony, for your continued contribution to our webinars. I thank you for that. And of course, today's presenter, John Lahiff, who is Associate Director of TMS Training Solutions, but principally owner of Aerodrome Services, specializing in AGL and ground traffic management, consultancy, design, and operational applications, and known to many of you. So without any further ado, I'd like to kick off, and John, if you'd like to make today's presentation. Thank you.
Yeah, thanks, Robert. I'll kick it off. So I think some of you will know me, some of you may not know me. So myself, I'm an AGL consultant, designer, trainer, and I own a company called Aerodrome Services, which you'll see there. So I wanted to there's a lot of AGL design criteria, the application data is set out by ICAO, but there's what's in the aerodrome design manuals. But how do people actually, how do you apply that simply? Or how do you get to understand it? So I wanted to show some of the design methods I use, looking at some of the examples in ICAO, and how you can follow these and educate yourselves to be able to implement the design. So in this webinar, as I said, a lot of the ICAO application data was covered in webinars 2. We also looked at the PAPIs in 7 and 8, and the last webinar 9 was compliance and serviceability. So I'm not going to go into every lighting system and every spacing and every installation tolerance, because anyone who's familiar with design will know that you're not going to fit this in a nice 45-minute presentation. So I'm just going to look at specific examples. So I'll look at first, you know, how we define the AGL design based on the client requirements, because we don't always have a complete tender package with listing what the client needs and wants. Sometimes as a designer, you have to go and propose your own design. I'll take a look at the various stages of design. Then what information is available to the AGL design. So where I source information, and then where sometimes you have to kind of fill in the gaps. I'll take a look at some AGL design methods and calculations tools that I use. As I said, everything that I show here today is pretty much, I'll take it from an ICAO document and just show it as an educational live sample. So at least afterwards you can go back and compare the two. Some equipment selection. So when you're selecting equipment, just some things to be aware of, like compatibility between systems. And then at the end, we'll look at ASMEGs, Advanced Surface Movement Guidance Systems, follow the greens, ILCMS, Individual Lamp Control and Monitoring Systems, and what kind of design considerations we have for that. And there's a couple of videos at the end if time allows. Spare here 1 sec, sorry. So this slide shows, this is coming into defining the client requirements. So this shows the various stages of how we implement an AGL engineering system, the life cycle. So first, the requirements will have to be defined. Then you may need a business case, who's going to define what's required, the commercial aspect. Then we're into the consulting and design, the specification. We'll select the systems that we want. It'll be reviewed, installed, commissioned. And then once it's all signed off, then it's going into the operation, maintenance and phase. And then the whole process will repeat itself as systems become out of date and they need to be renewed. Okay, so defining the client requirements. So depending on the job, sometimes I get a wide range of jobs I've worked on, from very, very small to very, very large. Sometimes they're greenfield, sometimes they're brownfield. Greenfield means it's, well, as it sounds, it's just a brand new airport built in the, so it's a blank canvas for the design. With a brownfield, you have to look at what systems are already there. So what kind of installation is already on site? So if it's an airport and maybe you're putting in a new runway, I'll always take a look at what's there on the existing runway. So if the approaches are Calvert or Barrett types, when I'm proposing an approach for the new runway, I'll look at what's there existing. There's no point in trying to go with something completely different than what's there, because you'll run into issues with approval. You'll get a lot of pushback. The history and the life cycle of the installation. So how long is it there? When was it installed? What kind of as-built information is available to me? Most of the time, you'll never get good as-built drawings. You'll have to do a site survey and have to try and define these yourselves. Is there a technical specification? There might be a good tender package? What category of operation will this runway be? So this will define what lighting systems you need, what spacings we need, dependent on what traffic density. You may have a runway that has a low category of operation, but it's very heavy in traffic, so we may need systems to implement systems because of that. Are there any special design considerations currently used on site? So some airports have different ways of interleaving. You know, some, instead of just having 2 circuits, some might use 4 circuits across a system. Some might, for color coding, some might double up on the colors. So instead of having, for your green yellows, alternate green yellow, you might have double yellows, double greens. So there's different, some, they mightn't space the lights at the runway edge lights at 60 meters, they might space them at 30 meters. So there's different things, you got to check what's there. What regulations are applicable? So there's a lot of standards, but you can only really pick one that you have to work to. So is it a civilian airport? Is it a military airport? So are we working to ICAO, or is it a local regulator? Is it a CAA in the UK, or where I'm from in Ireland, the IAA, or whatever? When the regulator have done their inspections, has there been any compliance issues identified? So maybe there's additional signs needed. Maybe there's some systems, you know, maybe they requested to put in stop bars everywhere, a ring of red, something like that. And a lot of the bottom one is probably one of the most important ones, is the client budget. Everybody wants all these systems, and it's great to implement a full follow the greens ASMEG system with a fantastic ACDM control system, but these systems cost, you know, millions, tens of millions. So we have to be practical of what the client actually can afford. Okay, so here the different design phase stages and responsibilities. So myself, I've worked in all of these kind of stages. I've been with the client as a member of the client's party. I've been as a contractor on site. I've been an airfield lighting supplier, working for them doing the design. So I've come in at different stages. So like starting off is just kind of feeding into what was on the last slide. So to define the design requirements, have a review of what design is there, if there's any design. Was it an earlier design done for a concept, or the as-built? You'll have to do a site survey of the current installation. Is there an AGL design package? So is there a full, have we come onto the job and there's already, this is the master plan, here's all the layout drawings, here's the specification, and we can pick it up from there. And we'll have to engage with the airport stakeholders to look at what's the current conditions they're operating on, what are they lacking currently, where do they want to go. So we may have a case of, you know, we may put in like infrastructure for future systems that we can't afford now, but we may be doing a Cat 1 airport, but we're not putting in Cat 2-3 lighting, but maybe our pit and duct system will be sized for category 2-3 lighting. Maybe we're installing ducts under the pavement, knowing that we're going to come back in the next cycle in 5 years, 10 years. So different stages of design. So the concept design is, this is to kind of define the budget, what systems we're going to put in, and what kind of quantities of lights we'll have. So with this is about 30% of the design. You'll see different percentages, but this is about it. So this is like laying out the lights, and then we get a basic definition of the circuit. So how many circuits will we have? Just to get an idea of how many CCRs we have, or whichever system we're using. Then we generate a BOQ to know what quantity of lights we'll be dealing with, what budget we can work with. Then this will lead into a tender package. So then this will allow then the contractors to bid. So once we start putting a tender package together, we'll start to firm up the circuits and the numbers of lights. So how many lights are on each circuit? We'll start to do generic design drawings. So it mightn't be specific to each location, but just this is what an approach mast will look like. This is what the foundation detail. This is what we're going to do inside a manhole. Then then when this is finished, then the tender BOQ. The BOQ will get tighter. We'll have to capture any contradictions against the tender technical documents. So anyone who's ever done these, you'll see if you're on the tendering side, sometimes you have an employer's requirements, you'll have a technical specification, and you'll have drawings, and you'll see a conflict between the three of them. This is quite common because a lot of the technical specifications, employers' requirements, they're recycled. Consultants will recycle them from other jobs, and there does be errors there that people just don't catch. So you can get things like, one document will say that the runway edge lights are spaced 3 meters from the edge marking. Then the spec might say they're 2 meters. Then you might open up the drawings in CAD and you measure 1.5 meters. So these kind of things are common. So then then review of the tender RFI. So as the tendering process is coming on, there'll be a lot of requests for information. Then you have to look at the return tender designs. What's becoming quite popular now is the design and build contract. So even with the design and build contract, you mightn't even get a tender package at 60%. You might only get the concept package, and then it's up to that bidding tender to bring it up to the 60%, to bring it back, and then based on that, what they've done, that's a part of their award criteria. And then whoever the awarded contractor is or the bidder, then they'll start working on the detail design, which would bring it up to about 90%. So this would be the final locations of all the lights, the specific detail drawings of what we need. So based on our approach types, what kind of profiles we're going to use, what's spacings, transformer housings, what goes into the manholes, how many transformers are going to be in each manhole, then what kind of calculations, there'll be circuit calculations, approach profile calculations, PAPI calculations. And then we'll have a BOQ that should be ready. They should be ready for ordering. So then this will go for final approval and comments with the client. And then we're into the final design drawings, the construction, the shop drawings will be issued. So then they're ready to go to construct. And then at the end of that, then we're into the testing, commissioning, the acceptance. So when we get then, we're into project handover, all the as-built drawings, the test results, the operation and maintenance manuals. And then we're into, you know, you may be developing the AGL maintenance plan, and then the AGL master plan, which is back to that life cycle slide. Everything will repeat itself. So just what kind of sources or information are available? So I'll always take a look at the aerodrome chart, the Aeronautical Information Publication, AIP, and just see what information is there. So what's currently installed, because most times you never get an as-built drawing. Then of course we have the ICAO annexes. The Annex 14 is the one we use. So aerodromes, Annex 14 aerodromes, Volume 1 is aerodrome design and operations, and Volume 2 is heliports, which I'm not going to look at heliports today. We have the design manuals, part 1 to 6. So 1 to 3 is kind of civil, 1 is runways, 2 is taxiways and aprons, 3 is pavement, then 4 is visual aids, 5 is electrical systems, and 6 is frangibility. There's also other ICAO manuals like the Airport Services Manual, part 9, which is about maintenance. And there's other manuals like the Heliport Manual, there's airport planning manuals. So there's quite a lot. There's IEC documents, the International Electrotechnical Commission. So they have a technical committee 97, which is all about airfield lighting. So I think they have about 5 or 6 documents currently published. The 61821 covers maintenance, and that's the one where we talk a lot about competence of people and authorized persons. That's all in that book. You have regional standard bodies like EASA in Europe, and Eurocontrol as well, which is an ATM. There's national ones like the FAA in America, but the FAA does a lot of detail in their advisory circulars, their engineering briefs, and their handbooks. So there's a lot of information that you won't get in ICAO that you'll have to go search in the FAA, and also look in other national regulators. So just an example of some regulators there: the UK, Australia, Transport Canada, the UAE. Then you may have a military installation. So we're looking at STANAG 3316 is the United Nations. The UFC is the Unified Facilities Criteria, not the fighting. And UK, you have the MOD, the JSP. There's various ones. Also, when we get into the PAPI, you'll need some aircraft design characteristics. In the Aerodrome Design Manual, part 4 at the back in the appendix, they list the data, the eye to wheel heights for certain aircrafts, but that document is 2004. So there's a lot of aircrafts in there. It's out of date. So you'll have to go and try and find these. For the Airbus and Boeing, you can find them. It's easy. But for smaller aircrafts, it can be quite difficult. Then the AGL OEM technical documents. So the manuals from the different suppliers, whatever system we're putting in, what's in their manuals? What specific criteria do we have to maintain? So all of these, for myself, I don't remember all of this information. I don't retain it. All I do is I just remember what book I have to look in and where to find it. So that's a good way to do it. So here's just a slide on, this has been covered in webinar 2. So what is an AGL fixture? That's just the definition from Annex 14. I won't read it out. The 4 C's of AGL, which is in the Aerodrome Design Manual, part 4. Configuration, color, candela, and coverage. So configuration is the pattern of the lights. The color is the color. Candela is the intensity of the lights. And then the coverage is like the beam spread of the lights, the horizontal and vertical tolerance, the towing of the lights. Then is the fixture unidirectional, bidirectional, omnidirectional? So when you're designing a system, the airfield lighting systems and circuits should be that if one system fails, we shouldn't result in a broken pattern or misleading information to the pilot. So we achieve this by interleaving and backing up power systems. So this as well, the compliance and the serviceability criteria was covered very well last week in webinar 9. So now I did this just a certain design criteria that just what's in ICAO, the application data in Annex 14, the locations, where I need to put these lights, when I need to put them, the characteristics per system, so the spacings, color codings, things like that. So when we're doing it, we have to select the right selection of the AGL systems. So based on our category of operation, what systems do I need? Based on that category of operation, what spacing can I use? What do I need? Different relationships between the systems and tolerances. So what I mean by relationships between the systems, sometimes you may have, if you've runway edge lights and they're spaced from on the marking or out to 3 meters, same taxiway edge lights on the marking out to 3 meters. If you take 3 meters for your runway edge and you take 1 meter for your taxiway edge, when both of them values are compliant as per ICAO, when you come to a taxiway intersection, you'd have a situation where your taxiway edge lights are inside your runway edge lights. So it's just like things like that. It's good to keep the meter in line or keep the taxiway edge lights in on the outside of the runway, further away. And what design resources are available for system, and what we did on the last slide. What design tools are used per system? So the next slides here is where I'll look at. I have a few design examples of different systems I've looked at. So I've looked at an approach profile calculation. I've looked at the PAPI, some circuit calculation, circuit parameters, circuit loading, and then I look at some interleaving and things like that. So as I said, it's hard to get everything into 40 minutes. There's a lot of things I've omitted, but I just try to I try to get as much in as I can. And even now, I'm conscious of the time as well to try and get through everything on the time I have. So here is just a little chart I made up that shows just the different tow-ins that are required per the different lighting systems. So when you order the lights, you'll order them with, you can see here on the, you know, these L's and these R's. So these lights will tow into the left. So as I'm looking out this way towards the approach, these arrows are towing into the left. Then as I'm looking in this direction, these arrows will tow into the right. So for threshold lights, they're 3.5 degrees. When you're in wing bars, they're 2 degrees. Runway edge lights, depending on the width of the runway, it's 3.5 or 4.5 degrees. Touchdown zones are 4 degrees. Supplementary approach lights or side row lights, they're 2 degrees. So mostly these lights tend to be inset, so you order them inset left or right. If you have elevated lights, you need to check with your supplier, is the 2 degrees covered in what they offer, or you may have to align your lights 2 degrees. And for the approach lights, all of the approach lights face forward, going out into the approach, but only when you have a distance coded or calvert approach. On the 750 crossbar, your grade, the furthest 2 lights are greater than 22.5 meters from the center line. So them 2 outer lights need to be towed in 2 degrees as per the requirements. And all of these towing requirements are in the Annex 14. When you see the photometric charts in the appendixes, you'll see this data listed. So for towing for some of the lights, some people, they buy the lights towing left and right. You align the shallow base parallel to the center line. Some airports I've seen, they order the lights without towing, and they like to align the bases. So they don't get mixed up. The maintenance people can't mix them up when they put them in. If you have a good installation and everything is done right, then yes, this can make sense. But in reality, guarantee that all the shallow bases are aligned 2 degrees. And I'm sure when you do your photometric test, you're going to have to core out some of it and do some rectifications. So here, before I do the approach profile, this just brings me into approach lighting. So in webinar 2, Keith covered this. So even as anyone who knows the approach lighting, if I went from the simple approach, different variations, I looked at the type A, which is the distance coded, the CL5B or calvert, or the Type B Beretta. If I went through all the variations across all the categories, I couldn't do it in 45 minutes, all the approaches. So here I'm just saying that I just put this in, that when you actually look in the Annex 14, they only recommend to put flashing lights when you have a Type B Beretta type. So you can see the flashing lights are there in they're there in yellow. But actually, you'll know, people will be familiar that there actually are culvert systems around the world with flashing lights on them. So that's where a national regulator overruled ICAO. Also, Keith spoke about this a little earlier, where serviceability of approach lights and other category 2-3 systems can be demonstrated, reduced approach patterns may be permissible. So I think Keith might talk about that a little later. So here on the approach profile, so I'll just show the methodology of how I do an approach profile calculation, what's in ICAO, and then how you practically do it when you have to do them for yourself. So ideally, all of the lights should be mounted at the threshold at that ground level, and you maintain them the whole way out. Practically, it's not so easy to do that. If you have rising ground, it's not possible. And then if you have a negative gradient, a negative slope, depending on how big the slope is, it's probably not possible either. So ICAO do give tolerances on rising and falling ground. So in the back of ICAO, it's in one of the appendixes right towards the very end. If you actually have a print edition of Annex 14, it's one of the pages that actually folds out in an A3, or it used to be anyway. I've been using the digital one for the last 10 years or so. So no objects are permitted to exist within the boundaries of the light plane that are higher than the light plane. So the light plane is how we do our lights. So where the lights set out, we're not allowed to have an object that sits above this. The exception being is the ILS localizer, because in most ILS localizers they're about 300 meters from the threshold, something like that. But you are, with the ILS localizer, there is a maximum height based on the distance you're allowed. So you're allowed a maximum of 150 millimeters, so 15 centimeters for every 30 meters. So that would mean, so if it's about 300 meters, so multiply that by 10, that'll bring you out, then you're at 1.5 meter above the light plane. So I've seen airports where they've actually brought it up and over the ILS. And then some will go, most it'll go through the light plane. So the frangibility of, if you see the diagram over here, so here this is from the Aerodrome Design Manual Part 4. If you see, only the top 12 meters of approach mast need to be frangible. So here you can see, I've just drawn in that this is assuming this is 12 meters. And then below you can see there's a rigid steel structure. So this is defined in the Aerodrome Design Manual Part 6. It's also written in Annex 14 and in the beginning of Chapter 5, I think, when we start to talk about the lights, it's written there. When we do, so if we calculate a light plane, if it's not perfectly level, you know, if you're allowed to do steps and things like that, you should keep the steps to at least 3 lights. So you don't have a zigzag pattern, just have nice steps. When I'll also show you the transverse. So when we look at the transverse, there is a slope allowed in the transverse, which is 1 meter for every 80 meters, which is about 1.25%. So here this is again, as I said, this is from Annex 14. So what ICAO allows for when we have rising ground. So either the ground is rising or we have a lot of obstacles. You know, we're going out over a road, over a highway, over houses that we need to, the light plane needs to be above these. So for the first 150 meters, lights are to be mounted at ground level. So keep the light for the first 150, keep them at ground level. And then we're allowed to step up a positive slope of 1 in 66. So for every 66 meters, we're allowed 1 meter height. So this is a 1.5% slope. This example is based on a full 900 meter approach. If we were doing a simple approach, which is only 420 meters, or possibly less if it's reduced, then I think it's only the first 60 meters you have to maintain this level. So if we have falling ground, so for the first 300 meter from the threshold, we're allowed a maximum negative slope of 1 in 66, so 1.5. Then after 300 meters, we're allowed a negative gradient of 1 in 40, 2.5%. If we have a category 2-3 system, negative slopes are not permitted within the first 450 meters from the threshold. So next example, I've taken how I plot out an example, and I've taken a category 2-3 system where I've observed this 450 meters. So this is not in ICAO. This is just pure. I've made this up so you can see the. Here are your distances. So your zero, your threshold. There's no lights at the threshold, obviously, out to your 900 meters. I've just taken distances where the ground is. I've just taken just ground heights, and you can see I've just dropped down. I've taken nice easy measurements. I'm dropping down half a meter, meter. And then here's my light plane in blue. And then this is the height from the bottom of the ground to my light beam axis. And then this is just showing my, if I have an inset fixture, if I have a pole, if I have a mast. So here the green, the ground is plotted. This red, this is my slope. So this is my 1 in 40, my negative slope. So this is the lowest I can go. So my blue line cannot go below this red line. And then here are my lights. So what I've done here is, if you saw in the ICAO calculations and earlier, a lot of suppliers of frangible mast, they make them up to 12 meters. Some make them higher in just their normal ones. Anything beyond, you need a rigid structure. So in the previous ICAO calculations, you'll see they based it on the 12 meters. So I've just taken it here. We're going to use 12 meter mass, so I don't have rigid structures, and then I level it off at that. So you can see the first 450 meters, all the lights, I keep all the lights at ground level. So for the first 300 meters or so, because I'll have a runway end safety area or something, the ground is pretty flat. These lights are inset, and then I'm into some elevated lights. So you'll see 300, 330, 360 meters. I have a pole here at 1.8 meters. So when you buy from a supplier, a lot of the times you can buy a base plate and a pole, and this will give you this goes up to a max of some are 2, some are 1.8 meters, and then after that you're into a specialist mast from the supplier. So here I've just taken it, I've calculated it across, I've gone down by the slope to maintain my 12 meters. So if you go here to 570, 600, you'll see my 12 here, and then I step it back out level. Now this example you'll see, and then I just do in Excel, this is where I've done my slopes. That's my negative slope. A 0.75 would have given me the 1 in 40. So this I'm dropping half a meter for every 30 meters. And then this one, then I'm just leveling out. So you can do this by what if calculations and goal seeks as well. If this was coming out at 12.5, I could do a calculation here to change the slope to get my answer. I just say that there are other possible solutions for this. So this is just one example. I could have taken all the lights level and said, the hell with the rigid, I don't mind having rigid structures. Let's do everything here at 14 meters and then keep everything perfectly level. I could have said, oh no, I want to maintain these lights. Them poles are way too high. I want to stay close to the ground so my maintenance team have easier access. I could have also followed the gradient going down as well. So here I've just looked at a transverse slope. I see I'm on, yeah, time is against me. So I won't go into the level of detail I did on the last one. The principle is the same. I've just taken it for a 300 meter crossbar. It's not the same system as the last example, purely because the last sample was all inset at 300 meters. So I've just shown the ground level, then the allowable 1.25% drop. So 1 in 80 over 1 meter over 80 meters. When you have a 30 meter crossbar, that's only giving you 375 mil, which is, you know, it's not a lot. So then I've just shown how to calculate that. Same principle. So here's the big one. Yeah, so the PAPIs were done excellently by Tony in webinars 7 and 8. So I just tried to have a look at it. There's a lot of information in the Annex 14, in the Aerodrome Design Manual Part 4. As Tony mentioned as well, the ICAO, or sorry, the CAA Cap 168 Appendix 6B is quite good. They explain the PAPI over, it's not over like 20 pages, it's over maybe 6 or 8 pages, and it's quite clear and easy to understand. So I will look at the calculation that's in the Aerodrome Design Manual Part 4. But first, whenever somebody ever asks you to do a PAPI calculation, first you have to know there's certain information you need to do before you have to have before you can even attempt the calculation. So you need to know what glide slope. Is it a 3-degree glide slope, which is the standard? Is it 2.5 degrees? Is it bigger? Is it 5 degrees? What aircrafts are we using? So if it's, depending on the aircraft, then we need to know the eye path, the wheel path, and then the eye path, the aerial height. Is there an ILS, yes or no? If there's an ILS, we need to know the ILS datum height over the threshold. What's the ground height of the threshold? Then I need to know the ground profile. So whether we're putting the PAPI on the left or the right or both sides, we need to know what is the levels of the ground at 15 meters, 24 meters, 33 meters, and 42 meters from the runway edge. Because the first PAPI is 15 meters from the runway edge, then 999. And then, so this kind of information would be, we'd want to know this from 200 meters down the runway, then 250, 300, you know, all the way down, depending on if our ground is sloping higher or lower. We want to know the locations of any intersections, taxiways within the survey zone. And then anything that came up in was there an obstacle survey done? And were there any obstacles that we may have to bring the PAPI back further to clear the obstacles? So here, this is, so acknowledge that this is taken from Research Engineers website. So Research Engineers is a PAPI manufacturer, for people who don't know. And actually the PAPI that they sell today is the original one that was used all them years ago by Tony. So they have, on this, they have a PAPI sighting estimator. So this is only an approximate guide because it doesn't take into consideration any ground heights or anything like that. But it's just good for you to get an understanding of what's kind of involved in the calculation and where roughly a PAPI would be if all of the ground was perfectly level. So in this one, I've just taken, you can select, is there an ILS, yes or no? Here I've selected no because in the calculation it's a yes. I've just taken a nominal 3. Here you have an option of 2.5 or 3. Why they give the option of 2.5 or 3? Because in the Aerodrome Design Manual, they list 2.5 degree glide slope, 3 degree glide slope for the different aircraft types. And then you can just select the aircraft. Now this is still, all of the aircrafts here are from the Aerodrome Design Manual Part 4, 2004. So there's a lot of aircrafts that just aren't in here. So you can see the angle for calculation is always 2 minutes below the angle for the B unit or the second unit. So here, if we don't have an ILS, the B unit will be at 2 degrees 50 minutes. So the design angle is 2 minutes below that. Here it's 2:48. So yeah, the calculation for the nominal position of the PAPI is based on the assumption that the PAPI units are at the same level as the runway center line. So you will also come into it where as well, there is a tolerance for like the transversely approach lights, there is tolerance for the PAPIs. So you get a situation where all the PAPIs are not in a line, they're all at different distances. So here you'll see this calculation. I will go through it in the next 2 slides, but all this is the Aerodrome Design Manual Part 4 calculation. And I've just taken it as an educational tool, which I use for myself whenever I have to do a PAPI calculation. I take it, I put it into Excel, I go through it step by step so I have an understanding of it. And I always review the Annex 14, review the Aerodrome Design Manual Part 4. And then once I'm happy with this, then I'll take this Excel file, I'll create another page, and I'll edit it as needs be depending on the different slopes and gradients and things like that. So I can do a calculation based on the conditions that I have. So the PAPI unit should be mounted not higher than 1.9 meters. And ideally all the units should lie on the same horizontal plane. If this is not possible, there is a crossfall allowed, and again it's a 1.5 1.5% crossfall is allowed across the units, so long as there's no more than 50 millimeters between each unit difference in height. So here, this is if you go into the back of the Aerodrome Design Manual, Chapter 8, Part 4, Chapter 8, you'll see this calculation. So I've just taken this, I've put it into Excel, and just to try and explain as an educational tool how you go about implementing the methodology for the PAPI. Some of the values are slightly different to his because I didn't have all of his, he rounds up and some of the, I don't have all the decimal points, but you'll see it's the same. So it's a calculation based on the PAPI with an ILS. So we're given the ILS datum height of 15 meters. The glide slope is 3 degrees. So here if you calculate the ILS origin, so I've put all the formulas here in brackets so you can see them. So how I got the answer for each. So ideally it's 286. Then I did the eye to aerial height. So this will be specific to each aircraft type. Here he had his smallest aircraft was Boeing 737. His largest aircraft was an A330. And what he did was he just took an average based on all the aircraft. So the average is based on a lot of aircraft that you don't see here. So he come up with 1.7 meters. Then I do, based on my ILS datum and my aerial height, I calculate the nominal position of the PAPI. So this will give me my, it's 318 meters. So then to calculate the minimum eye height over threshold. So here we're using, as I said, we're using now an ILS. So the B position will be 2 degrees 45 minutes. So we're two minutes below that, and so it's 2 degrees 43. So my MEHT, minimum eye height over threshold, will give me 15 meters approximately. So now checking for the wheel clearance. So now based on the different aircraft types, so what is the eye path to the wheel path for the Boeing 737? It's about 5 meters. A330 is 9 meters. So then depending on here, in the table in Annex 14, so for a Boeing 737, I have a desired of 6 and a minimum of 3. And then the same for the it's larger for the A300 because it's a bigger aircraft. So my even here, the MEHT, he just rounded it at 15. So you'll see it's written in his text. So then based on this, if I take my Boeing 737 from 15, I'm left at 9.82. This is higher than desired, higher than my 6. If I take my 9 from 15, I'm left with 6. So this is within range. So if we had have taken, say we wanted the desired for the H330, so then that would have given me an 18 MEHT. Then we would have, the Boeing 737, he would have lost harmonization with the, between the harmonization between the PAPI and the ILS would have been lost a lot further out because we took the much higher value. So the next part of the calculation then is the ground correction. So this is where it gets tricky in the PAPI calcs. So the first parts are like the example in research engineers. You can just, if it's just a perfect triangle, you can calculate it. Here we have to look at where the ground is sloping up or sloping down. If the ground is sloping down, that means the PAPI will be further away down the runway. And if the ground is sloping up, would mean the PAPI will be closer to the runway. So here he's given the threshold height at 60 meters. Then based on our nominal position, so you can see I've color coded everything. So the nominal we had earlier, I think was, let me go back, there you see it there, 318 meters. So at my nominal position, it was 318 meters. I have 63. So the difference here in elevation is 3.14 meters. So my ground is higher than my threshold height. So that means the PAPI has to move closer. So now we do a correction. So based on the difference, so my 3.14, my 2 degrees 40 minutes, we do a correction of 66 meters. So now once we do this again, what's the new amended position? Then we have to repeat the process again. We take the ground height at the new amended position and compare it against the ground height at the previous position. Then we have to go and then we do the same process again. So we do take the difference and we calculate where the PAPI needs to move again. So now we have a new PAPI position again. So first we got the 250. We went from the 318 to the 252, now to the 267. Now at this height, then we'll do another check again. When we do the check again, if the distance is less than 0.3, 300 millimeters or 0.3 of a meter, then we don't have to do any more refinement. You'll actually see in his calculation, he gets 2.3 here, 0.23 because he has a different value here, which he uses he has one value here, and then later on he uses a different value down here. So you'll be able to follow it. This 63.21, he calls it 63.31, I think, when he up here, but then down here 2.1, and then later on. So there are a couple of mistakes there as well, just as values were taken over. And now we do the correction based on the PAPI lens height. So this particular PAPI model is 0.3 meters. So depending on your model, it could be 0.6, could be 0.5, could be up to 0.9. You know, every PAPI one will have a tolerance anyway. You can go lower or higher anyway, because you may, depending on the sloping ground, you need that tolerance. So here we'll calculate the final PAPI position. So it comes in at, so we do the adjustment based on the, so it's the same as what we did here for the ground difference based on the PAPI lens. We get the final PAPI location is 261. Then you're able to do this back calculation, this is basically the calculation that was in the research engineers that got his one. This is just it here, this first part. So we'll do the final PAPI position, so the 261, 2 degrees 43, the ground height for the new PAPI, the threshold height, and then the lens height. So based on that, then we get an MEH of 15.24. So but once we know we're above the 15, we're above that minimum wheel clearance that we looked at for the A300. If we had been 14.99, we would have been too low for an A300. And then if this came out at 18 or something, we know we're too high for harmonization for the Boeing 737. So just this is as far as I go on the PAPI. So as identified in webinar 7 and 8 on the PAPI, the guidance material needs updating, and it's currently under review. So the PAPI methodology I've shown, and kind of it's based on the information that's available, and some of the information is quite complex. Even myself, I'm not an expert. I always have to re-educate myself how to do it, and that's just why anyone who wants to learn, take the information one in ICAO and put it into Excel and just try it. It would be the best one. Now I don't know if Robert's listening. So I'm conscious now. I've been talking for 42 minutes and it's a 45-minute presentation. So I'll crack on for a while till Robert eventually cuts me off. So the next part is I just look at, so some of these I'll go through these pretty quick. So this is just some circuit parameters. So this kind of stuff is in the Aerodrome Design Manual Part 5. So how to calculate the resistance of a primary cable. So here you'll need to know the resistivity of copper. So there's you'll find different values in different places depending on the ambient temperature and things like that. But this is the value that's in the Aerodrome Design Manual Part 5. So this is the one I'm using. So it's the 1.7 by 10 to the minus 8 ohms per meter by the length of the circuit, 5,200 meters. I use that because that's also using the Aerodrome Design Manual, and then divided by 6 millimeters squared, which will be 10 to the minus 6. So you'll get 15 ohms, say. So a rule of thumb, generally for every kilometer of primary cable, it's about 3 ohms. So then what's the losses in that primary cable? So any electrical people there, it's just the same, P is equal to I squared R. So our current here is 6.6 amps. The resistance we calculated in the last slide is 15 ohms or 14.9. So 6.6 squared by 15 ohms will give you 650 watts. And generally as well, for a, you get about 120 watts, 125 watts a kilometer, something like that as a rule of thumb. So here to calculate the insulation resistance. So there is a calculation to do this. So it's in the Aerodrome Design Manual Part 5. So you're allowed first, so to do the calculations, voltage divided by microamperes. So for every 100 meters of primary cable, we're allowed 1 microampere. And for every transformer in the circuit, we're allowed 2 microamperes. So again, the circuit length is 5.2 kilometers. We're testing it at 5,000 volts. Incidentally, I'll say if you do this, if you're testing at 1,000 volts, you get a completely different answer. Your answer will be less. So be aware of, if you're doing the calculation, what voltage are you testing at. So you should be testing at 5,000 volts. And say you have 100 transformers in the circuit. So what we do is we get a calculated value. This is the minimum value. So this is the worst case. So we divide 5,200 by 100. So that will give us 52 microamperes. Then 100 divided by 2 is 200 microamperes. So 252 microamperes. So 5,000 divided by 250 microamperes. I should have a division sign there instead of a bracket. I apologize. Will give you 20 megohms, say. So then the rule of thumb is, so then based on wet conditions, you should have 40 megohms. Based on dry conditions, you should have 100 megohms. So this is minimum values you should be looking for. A lot of new circuits you'll see in specifications, they want a minimum of 2 gigohms. Like the FAA only states 50 megohms for a new circuit. So if you're only commissioning new circuits at 50 megohms, you're going to run into a lot of problems. So you should be aiming for gigohms with new circuits. In the Aerodrome Design Manual Part 5, you'll see they do give some criteria for older circuits. So if a circuit is 3 kilometers long, then 50 megohms should be the minimum before you need to go out there and start rectifying the circuits. If it's 3 to 6, 40 megohms. If it's over 6, 30 megohms. So these are like the lowest values before you need to go out there and rectify the circuits. So the circuit parameters, again, this is the exact same as what we did for the primary to calculate the resistance. The only difference is you multiply by 2 because we have a 2-core cable, goes down, goes back up. So I won't do that one again for time. The resistance is the same, P by I squared R. So here's just a circuit loading calculation. So this is in the Annex 4 Aerodrome Design Manual Part 5, Chapter 8. So here they're talking about 45 watts, and then this is kind of based on halogens. So I will talk about LED considerations a little later if we get the time. And so in this lamp tolerance factor, what this means is if you buy halogen lamps, if you buy a 45 watt lamp, if they're made by Ostrom or GEC or whoever, every lamp is not going to be guaranteed to be 45 watts. There will be some sort of a tolerance in there. So this is this percentage. You may get some that are higher, some that are slightly lower. So we're just taking 45 watt lamps. This factor of 1.8, this is taken from the manual. We get 48.6 watts. If we have an ILCMS unit, so an individual lamp, if these are halogen lights, so they're not going to be smart lights, we'll have an external remote. He gives an example of 7 watts. The newer generations, they're down about 4 or 5 watts. Now there are older ones that are up 10 watts. So 7's a fair time. So we'll take we add the wattage of the lamp plus the tolerance, 7 watts. This 15.2 watts, that's our losses that was calculated on the previous slide. I see it there, Robert.
Carry on.
I'll stop. Yeah, the next section goes into interleaving. So, do you want me to stop there?
I think. Look, this is an absolute. I hope I'm speaking for the audience. This is absolutely tremendous presentation. I've been and we've gone into some great detail here. I think it's important we do the detail. But I think if we just finish this one, then we'll have to leave the interleaving till next week because there's another there's another 30 odd slides to go, and we're not
Yeah,
going to
I have 23 slides and 2 videos to go. Yeah. Okay. So I'll just summarize this one, this sheet, and then I'll that's me done. Okay. So yeah. So as I was saying, yeah. So we add the we get the fixture with the tolerance, the oil CMS. The 15.2 was calculated here. This was this 15 watts. We get 70 watts. So that's what's on our secondary side. Then we have to look at the efficiency of the transformer to transfer this load from the secondary over to the primary side. So he gives, for 45 watt transformer, he's giving 0.77. Depending on what brand you buy, I think they go from about 0.9%, 90% efficiency down to about 80, something like that. So then now we're up to 91.5 watts. So now multiply that by 40 fixtures, which is the example in the aerodrome design manual. This 649 watts was the primary losses we calculated a few slides earlier. So then this will give us a loading of 4.3 kilowatts. So then we'd have a 5 kVA CCR. If we're applying a factor of 20%, 1.25, we're up to a higher percent. So you can see by doing the calculation, even though we had a 45 watt lamp, you can see that if we had to put a 45 watt transformer, we would have been in trouble. So yeah, that's, I'll stop sharing now because I knew I wouldn't get through it. So that's pretty much me. I hope, Tony, I didn't go kill the PAPI too much. But thanks everybody for listening.
No, that's absolutely brilliant, John. Really, really interesting. And I hope, I know we didn't plan to go into a second week, but clearly we have more material we have to go through there. And I hope you, in some way, shape or form, ideally doing it yourself, will be able to present that next week. But we have, we're at 3 o'clock almost. We have some questions, well, a number of questions, and I'll try and do as many as I can. I've been rightly scolded by our teacher here, Mr. Costel, who's pointed out that we all have busy schedules, and you have busy schedules, guys. You've come on, you've given us an hour of your time already, and we don't want to run over. All your questions will be answered on the website, so you will get answers to your questions, whether we cover them now or not. But just quickly, I will ask some of the questions to our panel. Tony, first of all, is a threshold wing bar mandatory requirement for runways, or runways generally, or runways with a displaced threshold specifically?
Threshold wing bars are an alternative in some ways to the threshold bar, the green bar at the end of the runway. That's the primary cue, and certainly in low visibility, frankly, having done a lot of low visibility landings down to 100 meters and less, quite frankly, you don't see the wing bars in those conditions. The thing that makes you feel happier is when you actually see a green bar go under the nose of the aeroplane. You're landing on a runway. The wing bars are too far out really to be of any use in really low visibility operations. But of course there are operational scenarios where it's very difficult, perhaps or more difficult, to put a threshold across the end of the pavement, as it were, but it's feasible to put it into the soft. So I think the fact that there are some options there is the best thing. You do want something green there that says here is the start of the runway, but my preference would always be to have the end of the paved area. That's where I would put my green lights for preference. I don't think, if it's there, I don't think you lose anything by not having wing bars.
Right, thank you, Tony. Osvaldo in Mexico.
There, at the moment, one of the things that we find seem to be, best practice is when we displace the threshold from the start of the pavement or the start of the usable part of the runway, is when we displace a threshold for whatever reason down the pavement, then the use of a wing bar becomes a little bit more useful to the pilot because of the other lighting associated with the runway when a threshold is displaced. But
Yeah, that was
100% correct in what he's saying, you know?
yeah, that's what I was saying really. The general case is you don't need the wing bars, but there are cases where it helps you. Otherwise, you know, practically a bit difficult to put the threshold marking at the end of the pavement, as it were. So there are cases where it is very useful.
Yeah, but the key is it's not mandatory.
No.
John, a question from you from Osvaldo in Mexico. Good morning, Osvaldo. Good to see you again. Osvaldo would like to know from you under which circumstances we can substitute taxiway edge elevated lights for unlighted taxiway markers.
Generally now with the whole there's a thing called the sea of blue effect, where if you have too many blue edge lights across all the taxiways and all the spacings, it's very hard for the pilot to see the clear delineation of each of the intersections. So now it's with most airports now that they're like certainly hub airports where they're going to taxiway center lines everywhere. We're only putting the edge lights on the corners. So just on the corners and on the intersections. So when you get into the longer straight sections, like these long parallel taxiways, that's where they're starting to put them. But if he doesn't have center lines, then he's going to have to keep the blue lights. But if he has center lines, then he should reduce them down, especially if there's a lot of taxiways. It's very complex to avoid the sea of blue.
Thank you, John. Mohammed would like to know what are the different types of Cat 2-3 approaches, and how do you decide which type is most appropriate for your design? John.
So for category 2-3, there's two basic patterns that you'll have. The category 1, so the type A or the type B. I would go for the type B, which is the barrette, because you're allowed to supplement that with flashing. Where depending on the part of the world, the Calvert is the standard. Right, the Calvert is older and it had that kind of roll guidance at all the bars and it stopped at 300 meters down the runway. When this is not as applicable anymore, so I would go for the barrette type, with barrettes of 4 lights, 4 rows of side row lights and with flashing lights, and if needed, flashing lights at the threshold as well, retail lights as well. But it depends on the airport. As I said earlier in the presentation, if the whole country is Calvert, you're not going to get a barrette in there. You know, so you got to look at what the local regulator has as well.
Anything to add, Keith?
Yeah. One of the elements is probably on a commercial basis. You know, from as John rightly says, you know, around the world there's still a lot of countries that define Calvert as their preferred option, and that really comes from the old British days. You know, in the Commonwealth days, whereby, you know, it was directed and they followed suit accordingly to what they did in the UK. But of course, those times have long gone. And if you're looking at a barrette system now, as compared to a Calvert system, when you're looking at category 1 commercially, the number of lights, you know, hence commercially, is pretty much the same. But when you go to Cat 2, Cat 3, then with the addition of those red side row barrettes or supplementary approach lights, and together with the number of lights on the touchdown zone, because that goes hand in glove, then the actual number of lights on a Calvert package is much higher, the number of lights, than it is on a barrette package. So clearly, you know, if you're looking at purely on commercial grounds, you're going to choose a barrette. Okay?
Can I just say something about that? It just occurs to me that Calvert probably has advantages from a piloting point of view in Category 1, in clear visibility, and in Category 2 and 3, where frankly you don't use the outer part of the culvert. You're looking at that in a 600 meters where the red berets are. That's standard anywhere. And so for Category 2 and 3, those are your references. But in Category 1, and we tend to forget this these days, according to Category 1, you can be significantly displaced to left or right of the runway and still be compliant as a Cat 1 system. And with the coming into operation of GPS approaches, we may put pilots back into the era, which they don't have now with ILSs and current autopilots. They tend to come down the center line pretty well lined up. But it's perfectly feasible and permissible to use Category 1 boundaries. They're in Annex 14, where at 200 feet, you may be displaced lined up with the edge of the runway. You've got to make a significant S maneuver with very few references, and you need good roll references there. A Barrett won't do that for you. So it's a funny thing, the short end and the long end, yeah, Barretts are fine, but there's an intermediate state, which I guess a lot of airports and runways will be in the sort of Category 1 regime, or the bottom of a non-precision approach, cloud break situation, where the roll bars of the culvert are actually very useful and add to the safety of the operation.
Right, good, thank you. Question on taxiway lighting again. We know interleave circuits are required for runways. Are they required also for taxiways? Are they a requirement?
No. No, I actually had, if we had time had it permitted, I would have got onto that. I look at the different interleaving and what systems are not. But no, it's not required for taxiway edge lights to be interleaved. I have seen them. I've seen them interleaved in airports. But it's
well,
we
we won't steal your thunder for next week. But, okay. And also, you talked a bit about toe-in design, and I've been asked specifically which ICAO document. Do you recall which ICAO document provides guidance about toe-in chart design? So where can you see all the toe-in? I mean, I know it's in.
It's in the so in Annex 14 in the appendices where you see all the photometric charts, the isocandela diagrams. Under each particular light, it'll list what if there's any toe-in criteria or alignment criteria. It's also written. It's in the I think in the body of for each section. It's in there as well. But in the isocandela diagrams, it's there.
Right. We've been asked if we can provide the PAPI Excel calculations by email. Well, we'll be putting the presentation in there. Do you have any objection to us putting an Excel chart there?
Yes.
Or we actually compromising your work there? Because
no, it's not. There? I'd say no.
It's the PAPI calculation and as it's shown in the annexes require to be relooked at and revisited, and to give somebody direct guidance in the form of an Excel sheet, etc., to actually do a PAPI calculation. Remember, the PAPI is the direct influence on flight safety in the most critical part of flight, and therefore the PAPI calculations need to be done by someone who knows what they are doing.
Right. Okay.
Absolutely. I think my feeling is that if we revisited the material in Annex 14, the Aerodrome Design Manual, we could greatly simplify the basic calculation as to where the nominal PAPI origin is. But that can be almost universal application. But the actual sighting, allowing for crossfalls and so on, will have to be runway related, and there you need someone who is competent to do that. And you know, your specialist, your consultant you call in, who can do that calculation for that runway.
Correct.
Thank you. John, yeah, congratulations from many people. I see Wayne is congratulating you here. He's asked a couple of questions as well, though. So what limitations do you need to consider for ILCMS technology, especially for communication speed, distance, environment, straights, bends?
I do, in the next half, I do talk about ILCMS requirements. I don't go into that last part about bends and things like that, but I do list what you should consider when you're doing an ILCMS design, because when we get into follow the greens and considerations for LEDs and things like that. So I could say I'll answer half of it next week, and then the other half we can answer by email.
I think,
Well,
may I say that, remember that the requirement for individual light switching and then onwards to using that in surface movement guidance has, over the years, as it's been progressively introduced, and everybody has looked at still using the 6.6 amp primary circuit as the carrier or to introduce a remote switching facility within that system. And some use power line communication, others have used an individual control line to those remotes that we put between the transformer and the light fixture. And as we know now, some of that technology has now gone into the light fixture itself, but we're still using the 6.6 amp system. So there are other technologies coming forward which replace the 6.6 amp system, specifically advantageous for individual light control and monitoring and surface movement guidance. And so, you know, it's a big subject. It really is a big subject. And technology moves on pretty quickly.
And so big, I think, as John explained when we started today, it's much more than we could really, we could go into detail within 1 hour, but so much so we couldn't even go through one presentation in 1 hour. So John, I apologize. John was adamant before we started today we wouldn't go into week 2, but I think we've almost got him over the line.
No, I wasn't going to make a new presentation for week 2. As long as the work is done.
No, the work is done, and done very well. So I bear witness to the participants on this call who, in spite of running quarter of an hour over, have not been dropping off. So thank you so much, John. Thank you, Tony. Thank you, Keith, again. Excellent week. And week 2 of AGL design methodology will be same time, TMS Tuesday next week. So thank you very much. And I look forward to seeing you all. And we will, of course, be posting answers. Thank you, gentlemen and ladies. Goodbye.
Thanks.